Good morning, students. I would invite Prachi ma'am to start the session.
Hello everyone, good morning. Yes, Omka, how are you? So, uh, so Omkar, first tell me. So first, what we'll start is we'll just do a quick revision of whatever we have done, and the other part is that when we are learning about the dual nature of electromagnetic radiations, then in starting things may look little confusing, right? Which is very normal. So the important part is to ask if you have any questions or if you have. Second part is that revision. You can unmute your that way we can interact, and I'll be asking you few questions and we'll try to revise whatever we have, or else if you are not able to unmute, then you can interact in the chat. So if you are there, then try to interact in the chat so that I know, so that we can do a quick revisions where you will have to tell me the answers. Yes. So, Omkar, so what did we start with? So what were the developments that leads to the Bohr model of atom, and what are we learning right now? What is it that we are learning right now? So basically, there were two developments which we have to learn so that we understand the Bohr model of atom, right? Which is the dual nature of electromagnetic radiation. Another one is the experimental results regarding atomic spectra. And what is it that we are learning right now? Can you unmute yourself? Is that possible? If that is possible, it's better if you will unmute yourself. If not, yes, then we have the option of chat. Yes, what is it that we are learning right now? Okay, no problem. You can interact in the chat. So, what is the topic that we are doing right now? Yes, I am waiting for your response, and then we will revise whatever we have done so that we just know how the story is going, what were the things that were happening, and what is the sequence that we have to follow to understand the whole concept of dual nature of electromagnetic radiations. So what is it that we are learning right now? So if you, yeah, revision I'll do, but you will have to tell me, okay, basically, what we are learning about is we are learning about the developments, right? So basically, we have to learn about the two developments, which is the dual nature of the electromagnetic radiation and the experimental results regarding the atomic spectra, right? These are the two topics that we have to deal with. Now, you have to tell me among these two topics, which is the one that we are doing right now. Obviously, we'll do the revision for sure, but yes, you should know which is the topic that we are doing right now in the class, or did in the last two sessions. You should know that much, that what's the topic that is going right now in the class. So right now we are learning about the dual nature of the electromagnetic radiations. So when I say dual nature, then here we have to study about the uh, wave and the particle nature of the electromagnetic radiation. Then the next thing is, what are these radiations? What are electromagnetic radiations? So these are the radiations which we commonly see around us. They exist around us, right? For example, radio waves, microwaves, X-rays, ultraviolet rays, visible light, gamma rays, IR rays, right? Infrared rays, which is infrared rays. So the first thing that we should understand is how these waves are generated. So they will be generated when any charged particle it gets accelerated. So whenever any charged particle is getting accelerated, then there is a generation of the alternating electric and the magnetic field, which is traveling in the space. So basically the electromagnetic waves, they are the combination of electric and the magnetic field traveling in the space, right? So what is it that the electromagnetic waves consist of? And then what are the properties of the electromagnetic waves? So in the electromagnetic waves, the electric and the magnetic component, they are perpendicular to each other. They are perpendicular to each other and to the propagation, to the direction of propagation of wave, right? So what is happening here is, so we have electric field like this, magnetic field like this, or you can take the other way around. These are vibrating like this, and the propagation of the wave will be in this direction. So yes, both of them, electric field perpendicular to perpendicular to each other, and that's how they that's how.
Your video is not clear. Video and audio. Ma'am, you are not clear. Please wait for a few seconds, students.
Am I audible now, ma'am?
Yes, ma'am, now you are audible.
Okay. The networks are not that good today actually, because there is a lot of rain that is happening.
Okay, okay, ma'am.
So what I'll do is, today I'll keep my, is it okay if I keep my, don't switch on my video?
Yes,
Because
it's
in
fine,
that
ma'am.
a
Yeah,
lot of, yeah, the
it is
networks
very
are
much
weak
network.
today. Yeah.
Yes, yes, ma'am. That's okay,
The
ma'am.
voice breaks, then do let me know, ma'am, okay?
Okay, sure, ma'am.
Yes. So yes, we have Gayatri also with us. So Gayatri, can you unmute yourself? because this portion gets little complicated when we are learning, that is learning about the dual nature of the electromagnetic waves. It can get confusing in the starting, so it's very important that you should know what are we learning and how the things are going, right? So Gayatri, if it is possible, please unmute yourself. Yes. So, or else, Gayatri, you can interact in the chat, and it would be great if you can unmute yourself so that we can interact and revise whatever we have learned, and I can know what is it that you have understood in the last two sessions about the electromagnetic waves. So basically, what we are learning is we are trying to understand what how did the scientists came up with the concept that okay, earlier when people were explaining things with the classical physics or whatever laws, Newton laws we knew, so they used to apply those laws and they were able to explain most of the physical phenomena. But yes, with the time, like around 19th century, mid of the 19th century, there were many things which were not, so scientists, they were not able to explain them with the help of the classical physics, right? And one among them was the experiment that we discussed last time, which is the black body radiation. Correct. And also, I have told you, yes, there were few things which were not explained by the electromagnetic theory, right? Which were not explained when we are considering the radiations as wave. What were those things? Those were the black body radiation, photoelectric effect, variation of heat capacity, and the line spectra of atoms. And one by one, we will try to understand what exactly was happening there, which they were not able to explain when they considered the radiations as wave, right? And from there on came the concept of quantum mechanics, right? So overall, the conclusion is that we can't explain the things which were happening on the molecular or the atomic level by using the classical physics. So basically, we say that at microscopic level, when we go to the level where we are studying about the molecule, so we say, okay, we have reached to a microscopic level. So the Newton laws, or we say the classical physics, was not applicable to the microscopic things, which is basically what was happening with the molecules and the atoms, right? So that's the reason that the scientists came up with the new theories, with the new hypothesis, and this started the beginning of the quantum mechanics. So yes, the clarity of this concept is very important. Yes, it may take you some time to digest it, to understand it, to accept it. It may get little complicated in the starting. So we'll just quickly see what did we start with. The first thing that we started with is that we learned about the wave nature of the electromagnetic radiation. And in that, we learned that the waves, the radiations, they will be emitted whenever your charged particle, they are oscillating. And as you may know, atoms, they have electrons. So yes, of course, whenever I am providing any energy or the electrons in an atom, they will be vibrating, there will be a emission of energy. And what are the properties of the electromagnetic waves? The properties are that the electric and the magnetic field, they are perpendicular to each other, and also they are perpendicular to the direction of propagation of wave. And the other thing that we learned is that electromagnetic waves, they don't require any medium for their propagation. As we know that we are receiving light from the sun and there is vacuum in the space, right? So yes, these waves, that is the electromagnetic waves, they don't require any medium. And the visible part is a very small part of the spectrum, right? So there are lot many radiations that exist around us, which we say as the electromagnetic radiations, right? Which ranges from gamma rays to the radio waves. Now, can you quickly tell me Which one will have more frequency, gamma rays or radio waves? Yes, Omkar and Gayatri, you have to reply in the chat. Only when you reply, I would know that yes, you have understood the concepts. So here you will have to answer some of the questions which I'm asking, which is which one will have more frequency, radio waves or gamma rays? What do you think? Which one will have more frequency? Yes, the gamma rays have more frequency. What about the wavelength? What about the wavelength? So yes, so Gayatri and Omkar, yes, the gamma rays have more frequency. And what about the wavelength? Which among these will have more wavelength? So which among them will have more wavelength? Yes, you have to be quick with your answers. Yes. So the radio waves, they will have the more wavelength. As you can see here, that as I am moving, the wave is becoming narrower and narrower. So from here, what I can conclude is as I am moving from radio to the gamma rays, here the wavelength is decreasing, frequency is increasing, and energy is also increasing. So the gamma, X-ray and ultraviolet rays, they are quite harmful for us, whereas radio waves, which is basically used in the communication purpose, which are also used whenever we are using the mobile phones, right? So they are not that harmful for us. So if this is what we have learned. This is the whole electromagnetic spectrum, which is from radio waves to the gamma rays. And yes, these are all the electromagnetic radiations, where the part that we see with our naked eyes is a very small part of a light which we see with our naked eyes. Apart from that, yes, we have radio, micro, infra, ultraviolet, X-ray, and the gamma rays. Now, yes, here you must remember what is the range for the visible part, right? So the range for the visible part is from 400 to 750 nanometer. It is from 400 to 750 nanometer. Now, how do we define the wavelength? So, the wavelength, it is the distance between two consecutive identical points. It is the distance between two consecutive identical points. Similarly, we learned about the frequency, which is the number of waves that are passing through a particular point in a second. Wave number is the reciprocal of the wavelength, and also the maximum displacement of a wave from the particular axis is what is the amplitude. And how are these all related to each other? You have to quickly tell me what is the formula that we learned which relates the speed of light, wavelength, and frequency. How do we relate the wavelength, frequency, and speed of light? Yes. Yes, Gayatri. And Omkar, how do we relate the frequency, wavelength, and the speed of light? So what is the speed of light? The speed of light is 3 into 10 raised to the power 8 meter per second. And how do we relate the speed of light with the frequency and the wavelength of the electromagnetic radiations, or for the wave, how is the frequency and the wavelength related? Yes, you have to remember the formulas, right? It's very important to remember the formulas because mostly you will be getting the questions which will be based on the formulas that we will be learning. So you have to revise the things that we are learning. So how is the speed of light, wavelength, and frequency, they are related to each other? I think this much of a time is enough to type in the chat box, right? Simply you can write it. Or else you can unmute yourself and answer this. If your network are good, you can quickly unmute yourself and answer the question so that we do a quick revision, by which I know, okay, you have understood whatever we did in the last class, and then we can move on to the new concept. Because yes, these concepts are little complicated. They are little hard to understand at this point. But yes, once you understand it, then the whole thing will be very easy for you. So make sure that you are revising the things, you are keeping the formulas with you, because they'll be very useful in solving the numericals that will be coming further. So what's the relationship between speed of light, wavelength, and frequency? If possible, unmute yourself and answer it quickly so that we can again see what is the black body radiation. Do you know what's the relationship? Gayatri and Omkar, do you know what's the relationship between speed of light, wavelength, and frequency? If you know, okay. Right now, you don't remember what is the relationship. So, Omkar does not know what's the relationship between the speed of light, wavelength, and frequency. What about you, Gayatri? Do you remember what's the relationship?
Yes, ma'am.
Okay, what is the relationship between speed of light, wavelength, and frequency?
Speed of light is equals to wavelength into frequency.
Yes, I hope now Omkar has got it right. How the speed of light is related to wavelength and frequency. So it is the product of wavelength and frequency. Now this formula will be used in different ways, right? So where you can get a question ranging from asking you about the wave number to the frequency. Also, they can give you the frequency in this way, right? They can write cycles per second. So you should know that if they write cycles per second, then they have given you the frequency. Now, Gayatri, can you quickly tell me what did you understand when we were learning about the black body radiation? Can you summarize it? Whatever you have understood. Yes, Gayatri. You can unmute yourself. So keep it as a discussion. So yes, tell me what did you understand in black body radiation that we did in the last class?
Radiations emitted by
Hmm.
body.
Okay, what was happening there?
It absorbs the radiations.
And also, so what is if I say a perfect black body, how should it be?
The body, the body
Mhm.
will emits and absorbs the radiations, ma'am.
Yes, the body that can absorb all the radiation, and then after some time it can also emit the radiations, right?
Yes, ma'am.
Yes, so that's why the name is black body, because something which absorbs all the radiation would look black to us, right? Then after a while, this you might have observed in summers also, that it is not advised you to wear the black clothes, right? So what happens is, the black cloth, it will absorb the light, and then what happens after a while, it starts getting heating up, right? So basically the radiations that are being generated there whenever something gets heated up are the IR radiations. Okay, so still the IR radiations are the one which we can't perceive with our eyes, right? So it looks black only. But if it goes beyond IR radiation, then of course we can see a different colors, right? So if the temperature gets higher, then we will see a particular color. For example, if we take a iron rod and I start heating it, so initially it will be light red, then the color becomes a little dark, then finally it becomes a white, and then if I keep heating it, then it will become blue. Correct? So that's what how the color changes if you're changing the temperature. Now here we have the plot of what scientists they observed when they were heating the objects. So what they observed is whenever they were heating any object at a particular temperature, what happened is that the intensity of radiation it increases, it reached the maximum value. This is basically the lambda max, and then it starts decreasing, which is basically it starts losing its energy to the surrounding, right? So when I start heating any object, what happens is it starts emitting the radiations, which will correspond to a particular color. It reaches a maximum and then again the radiation decreases. Correct? So this is basically here. If I look at this portion, this is basically the visible portion. So this I can perceive with my eyes. But along with the visible light, the body is also emitting the other radiations which we can't see. So this is what was observed. And on the other hand, the expectations was that the graph should go like this. So this is, you should only understand this much. We should not go, we will not be going into much of the details, right? We will not go into the details of this curve. These all things maybe you will learn in 12th standard in your physics. We just want to understand, okay, what was happening, what they were expecting, and what did they observe. So yes, there was a difference between what they were expecting and what was observed. So the plot, it looked something like this, whereas they expected it to be like this. Now, the attempts were made to explain this, and the first scientist who was able to explain this phenomena, that is, the curve will be something like this. So basically, he just came with the explanation. He didn't perform any experiment or something like that. But what Planck did is he just gave an hypothesis, right? He just gave a theory to explain this plot, right? So what he did is he gave a formula, and then when he was putting the values, he got the same plot. So here we don't have to look at that formula, of course, but we'll see what was the conclusion of what he said. So what he said is that the matter, it emit and absorb energy only in discrete quantities. This is a very important point for us, because if I am considering the radiations as wave, then what I know is that there will be a continuous emission of energy, right? The wave will never end, right? So there will be a continuous emission of energy. So you can relate it to the stairs, right? You can relate it to the stairs. That is what he meant. So what he basically meant is only certain values of energy are possible. It can't be continuous, right? We are not having the continuous emission of energy. There are only certain levels that are possible. So it's like a stair. So I can stand on the first stair, or else I can be on the second stair. It's not possible to be standing on the stair. So I can't say I'm standing on the 1.5 stair, right? So it was the same thing with the energy. We can have energy in the multiples of h nu, which can be in the multiples of 1, 2, 3, 4, 5, and 6. But it can't be in fractions. For example, it can't be 2.5 h nu, it can't be 500.1 h nu, it can't be 2.5 h nu. So here he said that the energy is quantized. What it is quantized. It is in the discrete values. We don't have the continuous emission of energy. And with this hypothesis, he was able to explain the plot that we saw just now. So what you have to keep in mind is that Planck, what he said is that the energy is quantized. Only certain values of energy are possible. We can't have the continuous emission of energy whenever we are heating any object. So this is what he said. And then he gave the formula where he related the energy to the frequency. So what he said is that the energy, it will be discrete. When I say word discrete, that's what we meant, right? You will have the separate values, you will be having it in the levels, you will be having it in the levels how we have the stairs. It's not continuous, it will be breaking in between. And how will that breakage be? It will be in complete parts, you can't have it in the fractions. It will be the multiples of h nu, where we can have h nu, 2h nu, 3h nu, 4h nu. We can't have 1.5 h nu or 2.5 h nu or 3.5 h nu, right? So what he said is that the matter can emit or absorb energy only in discrete quantities. So it will be breaking in between. There is no continuous emission of energy. Discrete quantities, and the word that he gave is quanta. The word that he introduced is quanta in form of electromagnetic radiation. So the word that he gave us is the quanta. So let's understand how did he define quantum. So quantum he defined as the smallest amount of energy that can be emitted or absorbed. So it's like he was saying that energy, it was coming in packets. Energy, it is coming in packets. So only certain amounts of packets are possible. We can have 2 packets, we can have 3 packets, we can have 4 packets. I can't have 1.5 packet or 2.5 packet or 3.5 packet. And the smallest amount of energy that can be emitted and absorbed, so smallest amount will be this one. So the 1 packet we have is the smallest amount. He defined it as quantum. So that is the smallest amount of energy that can be emitted or absorbed. Now everything will be multiple of this. Now if you are taking 2 quanta of this, then it will be 2h nu. If I am taking 3 quanta of this, then it will be 3h nu. So what he basically said, that the energy will be in the multiples of h nu. It will be in the multiples of h nu. So he said that energy of quantum of radiation is proportional to frequency, and also it will be in the multiples of h nu, where n can be 0, 1, 2, 3, 4, and so on. Where your value of n, it can be 0, 1, 2, 3, and so on. Right? So yes, here he gave the concept that your waves, your radiations, they will be in the form of packets. They will be in the form of packets. And the energy, it will be in the multiples of these quantum. So we can have h nu, 1h nu, 2h nu, 3h nu. So this is the formula that you have to remember and keep with you. So that's how we will be calculating the energy of the electromagnetic radiations. So this is the formula for calculating the energy of the electromagnetic radiation, which is h nu. So this is the energy of quantum of radiation. This is the energy for the quantum of radiation. And what is quantum? Quantum is the smallest amount of energy that can be emitted or be absorbed. Right? Here, this H, it is equals to 6.626 into 10 raised to the power minus 34 joule second. The unit is very important. What is the unit? It is joule second, and this is known as the Planck constant. And the thing that you must observe here is, you can see that the constant, this is a very small value. It is 10 raised to the power minus 34. Right? So what does it mean physically? It means that yes, when I am looking at the light, it may look like a wave, but if I take a closer look, then yes, we will see that it is behaving as a particle also, where it is not in the continuous form. So whenever your light it is interacting with matter, it is behaving as a particle, and when it is traveling, then it is traveling as a wave. So it will be acting as a wave and it will be also acting as a particle. So if I'll zoom into it. So because it is moving very fast, because these particles, so what is happening here is I have these particles, right? If they'll move very fast, then they will look like a wave, right? So if they are moving very fast, they look like a wave. But if I'll take a closer look, or whenever I am seeing how the light it is interacting with the matter, then in that case we will observe the particle nature of these radiation, and that's how Planck was able to explain the black body radiation, where he considered that the energy will not come in the continuous manner, whereas the energy will come in the discrete quantities, and that will be equals to h nu, where nu is 6.626 into 10 raised to the power minus 34 joule second. The unit is very important. The unit of energy here is joule second. Now let's suppose somebody asks you what will be the energy for 1 mole, right? So what will be the energy for 1 mole? Then what you have to do is you have to multiply it with the Avogadro number. Then in that case the unit becomes joule second per mole. So once you multiply it with the Avogadro number, then you will get the energy in joule second per mole, which is a very important thing, because you have to see in the question where whether the energy is given for 1 quanta or is it given for 1 mole. I'll show you with the help of the numerical when do you have to take care that whether the energy is given in moles or whether the energy is just given for the 1 quantum. So energy can only be in the values of multiples of h nu. So basically this whole thing, how we can say it, that energy is quantized, that it will be in levels. It's like a stair that only certain levels are possible. All the levels are not possible. So this was the expectation that there should be a continuous emission of energy. But that was not the case. If I zoom into it, I'll see that this consists of the discrete values, and all the values are not possible. Only certain values of energy are possible. And this can only be explained when he was considering light as a particle, or when he was considering that light is coming in the form of packets. And he named one packet as 1 quantum, right? So the smallest amount of energy that can be absorbed or emitted. And how did he give the energy of 1 quantum? He gave it as E is equals to h nu. So this is how he explained the black body radiation. Is it clear to you? Yes. So did you understand what the Planck quantum theory, what did he say about the energy? Hmm. So basically the things that you have to keep in mind is the formula first of all. So that was the theory part, right? So most probably you may not get a question related to what is quantum or what did Planck say. Your questions will be based on this formula, which is the energy formula for the energy. So yes, first you have to maintain a sheet where the first formula that we learned in this chapter is for how we relate the speed of light, wavelength and frequency, right? And then the next formula that we have got is from the Planck's quantum theory, where he gave the energy of the electromagnetic radiation, and he defined the smallest amount of energy that can be emitted or absorbed as quantum. And he gave the energy of 1 quantum, which is equals to h nu, where h is the Planck's constant, and the value of Planck constant will be 6.626 into 10 raised to the power minus 34 joule second. But if I'm calculating it for 1 mole, then the unit will be joule second per mole. And how do I calculate it? I'll have to multiply whatever energy I'm getting with the Avogadro number. These are the things that you have to keep in mind. So overall, what he meant is that the energy, it will have only certain values. It will be only in the multiples of h nu. So how we can put it in words? We'll say that the energy is quantized. Energy is quantized. It is discrete. It is in the form, it is in the discrete values. And in that discrete values, only certain values are possible, which will be the multiples of h nu. All the values of energies are not possible. So basically, you can relate it to as like a stair. So we can stand on first, second, third, fourth, fifth, and so on those stairs, but we can't be in somewhere middle, right? I can't say that I'm standing on 1.5 stair or 2.5 stair or 1.75 stair. So that was the same case with the energy, that it will be discrete, it will be in the levels. It's not continuous like this. So this is not the case which everyone expected, but that was not there. So this hypothesis, Planck himself was not able to accept this hypothesis that light, it can be in the form of particle. So at that point in the mid of the 19th century, it was difficult for scientists also to accept the concept that light, it will be behaving as a particle. So yes, but yes, there were experiments which were not being, which were not, so they were not able to explain those experiments when they were considering light as a wave. So yes, light, it behaves both as wave and as an particle. So this was the hypothesis which was given by the Planck. Now, what are the kind of questions that you can get based on this, whatever we have learned? So till now, what we learned is, we learned about the black body radiation and the scientist who was able to explain this curve. There were many scientists who came and tried to explain this curve. They gave the formulas that should fit with this curve, but they were unsuccessful in that. So the first scientist who was able to explain it was the Planck. So how did he explain it? He said that yes, your light is a particle and the energy will be in discrete values. Your energy is quantized, and he gave the formula for the energy of the electromagnetic radiation. So what you have to learn from here is, what is the formula for the energy of the electromagnetic radiation? So energy is equals to h nu. So this was the first experiment which was only be explained when we considered light as a particle, which can only be explained when we consider light as a particle. So now you have to solve this question, that is, calculate the energy of 1 mole of photons of radiations whose frequency is 5 into 10 raised to the power 14 hertz. Photons means basically quantum, right? So you can call these particles, the one packet that is coming, you can call them as photons. You can call them as photons. So basically it is asking you to calculate the energy for 1 mole of photons. So you know what is the energy for 1 quantum? It is h nu. So it is asking for 1 mole. So it will be Na into h nu. So simply you have to put the values and do the calculation. You know the frequency, you know the Planck constant, you know the Avogadro number. So here, what is the unit that you will get? You will get joule second per mole. Joule second per mole. So this is the kind of questions that you can get, where you will be asked to calculate the energy, and maybe you would be given the wavelength also. So this I know, nu will be, so C is equals to nu into lambda. So nu is equals to C over lambda. So how can I write this formula? E is equals to Hc over lambda. This also you should note down, that E is equals to Hc over lambda. So now from here, The two formulas that we have got, E is equals to H nu, or we can write it as E is equals to Hc over lambda, where I know C is equals to nu into lambda. So these are the three formulas that you have to keep with you, where C is equals to 3 into 10 raised to the power 8 meter per second, where H is equals to 6.626 into 10 raised to the power minus 34 joule second. Now you can do the calculation based on whatever they are giving you in the question. If you are given the frequency, use this formula. If you are given the wavelength, then you have to use this formula. So now the formula remains the same, only there will be the variation in the numericals. So if this is clear, then I'll just give you a little glimpse of what we will be learning about in the next class. So the next experiment that at that time the scientists, they were not able to explain by taking the radiations as wave was the photoelectric effect. What was that? Photoelectric effect. So if this Planck quantum theory is clear, then quickly tell me in the chat so that I'll just give you a glimpse, and then we will understand in detail about the photoelectric effect and what was its conclusion, what they were expecting, and how the results were different from their expectations. And then Einstein, he came and explained this whole thing by considering whatever was said earlier, right? So basically the experiment, it was conducted by Hertz, but it was the observations, they were explained by Einstein. Yes. So if there is any confusion, you can ask me again, because yes, these topics are little, in the starting, you may find it little difficult to understand. So it's normal. So you can ask your questions, you ask as many questions as possible. There is no problem in that. So in next class, we'll be learning about photoelectric effect. So what was happening there? Okay, so Omkar wants me to explain the formula question. So see, what they are asking me, calculate the energy of 1 mole of photons of radiation whose frequency is 5 into 10 raised to the power 14 hertz. So hertz, when you see hertz, you know that what did they give me? Okay, they gave me the frequency, right? So what did they give me? So they have given me the frequency, which is 5 into 10 raised to the power 14 hertz, right? Now, Planck, he gave me the formula to calculate the energy if I know the frequency. That's what he did. He said that energy of one quantum, or if I say photons, right? You can use the word photon also for quantum. So E is equals to H nu. E is equals to H nu, where H is the Planck constant whose value will be 6.626 into 10 raised to the power minus 34 joule second. And this I know, so they have given me the value for this. This is the value, this is the energy for one photon. This is the value, a value of energy for one photon, or I say one quantum, right? But what they are asking me the value of energy for 1 mole. So 1 mole is how many particles? 1 mole is, this is the energy for one photon. Now, what is the number of photons I have? I have 1 mole of photon, which is equals to the Avogadro number, which is 6.02 into 10 raised to the power 23 per mole, right? So now, whatever energy I am getting, I'll have to multiply it with 6.02 into 10 raised to the power 23 per mole. So then I'll get the energy in joule second per mole. So you just have to do the calculations, put the frequency here, and you will get the value of energy. Is it clear, Omkar? Now is it clear how you have to approach this particular question? So you have to pay attention whether they are asking for 1 mole or are they asking for one quantum. Okay. Are they asking for one photon or one quantum, or did they give the value for just 1 mole, or they gave the value for one quantum? How will you identify that? Take a look at the unit. If you see the unit as this for the energy, then you should know that this is the energy for 1 mole. If you see a unit as joule second, then you must know this is the energy for one quantum. Understood? So these are the small things where yes, you can get confused in the exam. So pay attention to it. So just make a note in your notebook that yes, look at the value of the energy, whether it is joule second or joule second per mole. If it is joule second per mole, then the energy is for the 1 mole of quantum or photon. The understanding of the numerical is very, very, very important. And this is the energy for one quantum. And then you have to proceed further according to whatever they are asking in the question. So these are the things, these are the formulas that we have to keep with us till now, which is the relationship between frequency, wavelength, and energy for one quantum. And let's suppose if you are not given the frequency, you are given the wavelength, then yes, you have to use this formula and then you can do the substitution. Where you can give energy is hc over lambda, where we know the value for the speed of light and also we know the value for the Planck's constant. I hope this all is clear to you. If you have any doubts, you can ask. And what are we going to learn in the next session? So in the next session, we will be learning about the photoelectric effect. And then we'll see what were the expectation and how is it different from what they were expecting it to be. Right? This is also a very interesting experiment where the observations are little different from what was expected. So be prepared for tomorrow to learn about the photoelectric effect. And with this, we'll finish the first development, which is the dual nature of the electromagnetic radiations. So the combination of all these observations, with this, yes, the scientists, they accepted the fact that yes, light, it behaves both as particle and as a wave, which was little hard for everyone to accept this fact at that time, right? So they were not able to, yes, it was, they were little discomfortable to accept this fact that light behaves as both particle and as the wave. So yes, in tomorrow class, we'll be learning about the photoelectric effect. So yes, I'll see you in the next class now. So with this, we'll end this session and be prepared, solve the problems. So I'll be giving some 2-3 problems to ma'am. So just make sure that you send the answers for the same. Okay, see you all in the next class. Yes, Chandrika ma'am.
Yes, ma'am. Thank
Hello?
you, ma'am. Yes, ma'am. Thank you, ma'am.
Yeah.
The students, I have shared you the next class link in the group. You can join, students. You can join.